Hi everyone, my name is Nicolle. I'm a researcher at LMMP, and I will present my work entitled Foam Formation and Flow Diversion in Surfactant-Alternating-Gas Injection in Porous Media Micromodels. This work was conducted with Professor Marcio Carvalho. Water and gas are commonly injected into the reservoir to maintain the pressure and displace the oil towards production wells. In addition, we have the enhanced oil recovery methods that are the applied techniques to maximize oil production through the interaction between the injected fluid and the rock oil system. And we need to understand this interaction as fluid flow happens below the surface. So this flow process can only be imagined, but not fully visualized. To understand this displacement process, pore scale level imaging and modeling become increasingly important. Different methods can be used with their own advantages and disadvantages. One of them is the gas flooding. When we inject gas, the gas flows through the upper part of the reservoir, leaving a large amount of oil behind. This is an early breakthrough. And also we have the formation of these instabilities, the viscous fingers. When we inject water, we have the opposite behavior. So water flows through the lower part of the reservoir, also leaving a large amount of oil behind. In this third case, we first inject a slug of surfactant solution, then we inject gas. In this case, we are forming foam inside the reservoir during the gas injection. And foams are less sensitive to gravity and permeability heterogeneities, so it provides a more uniform sweep front here. And the success of this method highly depends on generation and stability of foam inside porous medium. In 2014, in the Lisa Bisval group, they visualized oil displacement with foam in a microfluidic device with permeability contrast. So they preformed foam in a flow focusing device, and then the injected foam here in this device. Foam flows through the high permeability zone, blocks this region, and then diverts the gas to the low permeability zone. Also in 2014, Salehi and collaborators studied surfactant alternating gas performance on oil displacement using bed packs. In 2017, Kamal and collaborators used the core flooding system to evaluate the surfactant type and concentration in gas sequestration efficiency. And in 2020, Wang and collaborators did a microscale visual investigation of water alternating gas injection. So most of the studies focused on pore scale analysis are concentrated in preformed foam, but preformed foam sometimes have an excessive injectivity reduction. So the surfactant alternating gas is a better solution in this case. And the surfactant concentration impact was only studied in core flooding system, so not visualizing the whole dynamics. The goal in this work is to visualize foam formation inside the porous medium during surfactant alternating gas method and understand the effect of surfactant concentration on oil displacement. To do that, we're going to use a micromodel. It's a 2D micromodel made with glass by Microneat. Here is a picture of the device. We can see that there's one inlet, one outlet. Here is how we can see the device in the microscope. We have two buffer zones, one in the entrance, one in the outlet. Here are the properties of the micromodel and the sizes. The fluids used in this case was the mineral oil, light mineral oil, the Draciol 7. Here we have the properties of the micromodel. The surfactant solution used was a sodium dodecyl sulfate solution. The critical micelle concentration was equal to 2.36 grams per liter. And above this concentration, we always have the same value for the interfacial tension. That was equal to 34.4 millinewton per meter. Here are other values of interfacial tension between the phases. The experimental setup consists of a syringe pump, a gas-tight syringe to inject the fluids, a pressure transducer to monitor the pressure, the micromodel, a stereoscopic microscope, and a computer to do the image processing. Here is how we can see the micromodel in the microscope. And we're going to do the image processing in these images. First, we saturate the device with the Dracul 7 that was dyed in brown color. Then we inject 15 per volume of the aqueous phase that could be water or surfactant solution dyed in red color. Here is the flow rate of the aqueous phase. Then we inject gas at a constant volumetric flow rate equals to 2 milliliters per hour. And we measure the pressure during the gas injection and visualize the flow dynamics. Here is a video showing the gas injection in a water alternating gas injection. So the oil is this brown phase here, and the water is this red phase. We're going to inject gas from the left to the right. You can see here that the gas remains transparent. We see that the gas percolates the micromodel and finds a preferential path. On A, we can see a picture taken after water injection, and we have 30% of oil remaining. In the second picture, letter B, we can see a picture taken after the gas injection, and we have 27% of oil remaining. The conclusion is that the gas flows through the same path as the water and not diverts an amount of oil, an additional oil. Comparing the pressure behavior, we can see that the pressure increases, reaches a maximum around 10 minutes, then decreases, reaching this plateau. Now we are going to add surfactant to the aqueous phase. Here we are below the CMC. We have 0.2 times the CMC. In this first picture, it was taken after the surfactant solution injection, and in this B, after the gas injection. We have a very weak flow diversion, and the extra oil recovery was only 4%. Here is the pressure behavior. The pressure increases, reaching this plateau. Now we are going to add surfactant above the CMC. Here is a video. In this case, we have 2.6 times the CMC. We can see the gas being injected from the left. And what we can see here is that we are forming foam. Here we can see many bubbles. We are forming foam inside the micromodel during the gas injection. After the gas injection, we can see here that the reduction in the oil, in the presence of oil, the oil remaining, was from 30% to 16%. We noticed foam formed inside the micromodel, and this foam was responsible for increasing the oil displacement. The pressure increases as well, reaching a higher value compared with the previous experiment, and also reaches a plateau here. Now we are going to increase further the surfactant solution concentration. Here we have 6.5 times the CMC. We can see the gas being injected from the left. We can also see foam being formed. And as we keep injecting gas, you're going to see here at the end of the injection, we have only a few oil ganglia remaining in the reservoir, in the micromodel. Now comparing the pictures taken after each step. The first one we can see after the surfactant solution injection, and on B we can see after the gas injection. In this case, we saw that much more foam was formed inside the micromodel, and the maximum normalized pressure here was a higher value. Now plotting all the curves in the same plot, we can compare the different values for the pressure. We can see that in this case, in the red curve, we have the higher concentration and also the higher injection pressure. This orange curve, we have 2.6 times the CMC. In the black curve, we have no surfactant. So the higher surfactant concentration leads to a higher injection pressure because of the higher number of lamellae that was formed. Now here we are comparing the amount of oil remaining after each step. Here we can see the concentration from 0 to 6.5 times the CMC. And we can see here that the percentage of reduction in the oil remaining increases as we increase the surfactant concentration. So this higher surfactant concentration leads to a stronger mobility control and a more efficient oil displacement. My conclusions are that for low surfactant concentrations near the CMC, gas flows through pores occupied by surfactant solution with very weak flow diversion. And the effects of foam become apparent when the surfactant concentration is increased. The lamellae formed was responsible for increasing flow resistance, diverting the gas to the oil-filled pores and displacing the trapped oil. Even though the interfacial tension values above the CMC are the same, the higher amount of surfactant allows a greater number of lamellae to be created. I would like to thank you all for the attention and thank the funding agencies.